Hello everyone, and welcome back again to the linear algebra component of the calculus and linear algebra series. In the previous video we introduced a small subset of the binary operators, namely the logical and, logical or, implication and equivalence operator, and we also proved a theorem, which was the law of excluded middle, that said that P or not P was a tautology. And in this video we're going to do something along similar lines, and we're going to prove some more theorems that are tautologies that are going to be particularly useful within propositional logic and allow us to say whether or not an argument is deductive or not. So our first theorem that we're going to look at is called Modus Ponens, which translates from the Latin to say the mode by which affirming affirms, or the mode that by affirming affirms. And we'll see why it's called that by just looking at the statement of the theorem. So the theorem says that if P and Q are propositional variables, then this overall compound proposition that looks a bit complicated is a tautology. In other words, what it's saying is if we take P implies Q and then compound it with P and take that whole thing and say that implies Q, that thing is a tautology. Why is this tied to the statement about the mode by which affirming affirms? Well, it basically says that if I have P implies Q and I affirm P, I confirm P, then it must follow that Q is true. So that's why it's called that in this way. How would I go about proving this? Well, I prove it in the usual way. I need to form a truth table. I need to take the valuation of this, and I need to check that the valuation is always true. And I can do that by looking at all its atomic propositions, which is just P and Q in this case, all the truth values of those atomic propositions, and all the iterations. So in this case, we've got P and Q, and we've got P is true, Q is true, P is true, Q is false, P is false, Q is true, and P is false, Q is false. And the first component of this we're going to look at filling out is P implies Q. Well, to fill that out, we need to look at these two columns here, because the pieces that form up P implies Q are P and Q. And we already know what the definition of that is by looking at our binary operator table from the previous video. In other words, it takes the value of true for the first value, then false, then true for the third value, and true for the fourth value. So it's only false in the second value. Now the next piece that we want to look at from our compound proposition is P implies Q and P. So to fill out this piece of the table, what two columns do we need to look at? Well, we need to look at the column P implies Q and the column P, because those are the two pieces in order to fill out the truth values of this column. So when is this true? Well, it's going to be true when the truth value in P implies Q is true and the truth value in P is also true. So that's only the case in the first row, right? Because we've got P is true and P implies Q is true. For the rest of them, we have at least one of them is always false, and therefore, because we're using the AND operator, all the remaining values in this column are going to be false. So what's the final value of the column that we're going to look at? Well, that's going to be the actual compound proposition we're proving is a tautology, namely Modus Ponens. So which two columns do we need to look at to prove or to fill out the entries of this truth table for this column? Well, we need to look at the column Q and the column P implies Q and P. So when is this going to be true? Well, thinking about our implication definition, it's going to be true when this P implies Q and P is true and Q is true, which is the first case that we've got there, right? So that's going to be the first entry which is true. And now as we go down the P implies Q and P column, all the values of that are false. And recall that when we've got an implication, if the initial thing is false, that can imply anything. So whenever the initial thing is false in the implication statement, that is always true. So the next three immediately follows have to be true because all our values in the P implies Q and P column are false. So what have we shown? We've shown that independent of the values of the truth values of P and Q, this overall compound proposition is always true. In other words, it's a tautology, and we finished our proof. So now let's look at some examples in which Modus Ponens is used. So these are a couple of examples here of Modus Ponens in action. So we take a kind of series of statements or propositions. First statement we've got here is, if it is raining outside, then I have my umbrella. So this is like the P implies Q statement. The next thing we take the P value, which is it is raining outside, and therefore I deduce Q, right? The third value, therefore I have my umbrella. So that's effectively using Modus Ponens, right? I've affirmed the values and I've therefore affirmed the conclusion. And when we use Modus Ponens, or whenever we construct an argument using Modus Ponens, we say that this argument is deductive. So let's look at another example. In this case, I'm going to take some false things. I've got if pigs can fly, then they have wings. The next statement is pigs can fly, and then I deduce hence pigs have wings. So this is another example of using modus ponens. This statement all holds, all these values, this overall argument is still valid, but the individual propositions here are actually false. But we've just seen that independent of the values of the propositions, the overall argument or modus ponens is always true. So actually this kind of brings a kind of smaller subclass or subdefinition within deductive arguments, that if we have an argument that uses modus ponens, then the argument is deductive, and if the component propositions that are inside modus ponens are actually true, then we say the argument is sound. So the example 1 is an example that would be sound if it was raining outside, for example. But example 2 is an example of an argument that is deductive, but it is not sound because the actual propositions themselves are false. And the next thing we want to move on to is the theorem about modus tollens, which in other words says the mode that by denying denies. So how do we write that one out? Well, again, we say let P and Q be propositional variables, and we take this kind of longer compound proposition, which says P implies Q, and now we suppose and not Q, and that implies not P. So you can probably see why this is saying that the mode that by denying denies, because now we take P implies Q, we say not Q, and therefore we deny not P. So that's we're denying Q, and we're saying that therefore that denies P. But again, we want to show this is a tautology. How do we do that? We need to take the valuation of this thing. So we need to fill out a nice truth table. This one's going to be a much bigger truth table. Again, our atomic propositions are still just P and Q. So again, we just take P and Q, all the truth values and all the iterations. And what's the first point we want to fill out? We're now going to fill out not P first, because that's our first unary piece of this compound proposition. What happens when we look at just not P? Well, we just take the column P, and then we just need to negate all the values in P, because that's what takes us to not P. So the first value takes true to false again, false to true, and false to true again. And then the next piece, the next column that we're going to construct is going to be not Q, because that's another piece of our compound proposition above. To construct not Q, we need to look at the column Q, and similarly again, we take true to false to true to false, and false to true, because that's again just our definition of the negation operator. What's the next piece we're going to take here? We're going to take P implies Q. So to look at P implies Q, we need to look at the columns P and Q. So we just fill out the entries of this, which are exactly the same as the ones we saw in the last video from our definition of the implication operator, namely true, false, true, true. Right, so this hopefully is the one that you can recall now from the previous video. And we now want to look at P implies Q and not Q. So which two columns do we need to look at to fill this out? We need to look at the column not Q and the column P implies Q. So we need to look at these two columns. And let's think about when that is going to be true. Well, with the AND operator, it's only going to be true when both the truth values are true. So the first one, we've got a false for not Q, so that's false. In this one, we've got P implies Q is false, so that's going to be false. In this situation, we've got not Q is false, so it's going to map to false. And the last one, we finally got both values are true, so this is the only one that's going to map to true. And then we want to fill out our last piece now of this truth table. So our column now is going to be filled with modus tollens, which is this kind of long compound proposition. Which pieces do we need to look at in order to fill this out? Well, we need to look at not P and P implies Q and not Q. So when is this thing going to be true? Well, it's true whenever the value of P implies Q and not Q is false, because again, from our definition of the implication operator, a falsehood can imply anything, and we always take that to be true. So that immediately follows that the first three values must be true, because we've got three falses in there. And then the last one, we just simply need to check, well, we've got a true in our P implies Q and not Q column. So we just need to check that indeed the corresponding truth value in not P is also true, which indeed it is. So that last value is also true. So again, we've shown that regardless of the truth values of P and Q, that this overall statement, this compound proposition, is always true. In fact, it's a tautology. So we finished our proof, and that is our proof of the theorem of Modus Tollens. Again, like before, we're going to look at some examples of Modus Tollens to see it in action. So let's look at our first example. Remember, this is the mode by which denying denies. So we've now got, if it is raining outside, then I have my umbrella. So it's similar to before. It's the same P implies Q statement. But now I'm supposing not Q, right? So that's just, I do not have my umbrella. So therefore, what do I deduce? I deduce that therefore it is not raining. So again, it is somehow deductive in some sense. So it's kind of just a different version of Modus Ponens. And in a similar way, let's look at some values, another one. So I've got, if I am my father's son, then I have blue eyes. So if I do not have blue eyes, it therefore follows that I am not my father's son. So this is an example of producing an argument from Modus Tollens. And although there are not some examples here in which my actual propositions are false, all of these could be taken to be true. It also holds similar to the Modus Ponens example, as we've just proven in our theorem, that independent of the truth values of the independent propositional variables, these arguments or these compound propositions are always true. So that's where we're going to finish this video. We've introduced Modus Ponens and Modus Tollens, which are useful to form some sort of deductive arguments and how we produce sort of arguments in mathematics or propositional logic. And what we're going to do in the next video, well, we're going to introduce the idea of the converse, and we're going to expand more about this last piece, this last binary operator that we haven't really gone into, which is the equivalence operator. So we're going to arrive at a definition of equivalence and see how this relates to the converse of a statement, which is going to be particularly useful when I actually want to show two particular propositions are in fact equivalent within mathematics. So thanks again for watching the video. Please read the material on the Moodle page afterwards, and I'll see you in the next video. Bye.